The latest data on Comet 3I/Atlas is forcing scientists to confront a reality where the standard rules of space no longer apply. We now possess some of the most detailed imagery of this object ever captured. And what these pictures reveal isn't just unusual. It directly challenges the foundational physics governing how comets behave. Furthermore, a new study from a leading astrophysicist highlights several more irregularities that current models simply cannot account for. We are observing tail formations that logically should be impossible this far from the sun's influence. We're detecting luminosity that defies all our forecasts. The very geometry of this activity points to major flaws in our understanding of thermal dynamics in space. So, what is truly going on with 3I/Atlas? And why is its persistent strangeness becoming the new normal? Right now, this comet is located approximately 186 million miles from our planet. To put that in perspective, it's sitting at double the Earth-Sun distance. Before we dive into the issues of mass dissipation and anomalous brightness, let's examine a feature in these photographs that breaks the most basic principles of cometary mechanics. This snapshot was taken by an amateur observer on November 22nd using a sizable half-meter scope, an instrument that gathers immense light to see faint, deep space objects. It displays a vivid glowing coma enveloping the core, with two separate defined structures streaming out. These are the comet's tails. One tail stretches an astonishing 3 million miles back, away from the sun. The second tail, however, points directly toward the sun and spans about 600,000 miles. Both maintain an unnervingly narrow, focused beam. Here is another image from just 2 days later. Despite the object being barely 15 degrees above the horizon, a notoriously difficult angle for observation, the identical structures are present. Multiple independent sources confirm this, verifying these are genuine features, not glitches. The strangeness lies in how tightly collimated these jets remain. The typical comet's tail diffuses and spreads, becoming fuzzy over distance. These stay coherent like beams from a lighthouse across millions of miles of void. So why is one tail 5 times the length of the other? The tail pointing away gets assistance. Solar radiation pressure and the solar wind both propel material in that direction. But the sunward tail, it must fight against those very same colossal forces. Every atom in that anti-tail is swimming upstream against a stellar hurricane. To form a 600,000 mile long structure while resisting the solar wind, the ejected material must be extraordinarily dense. Analysis suggests the mass density within this anti-tail needs to be roughly 1 million times greater than the density of the solar wind it opposes. That is not ordinary cometary outgassing. It is something entirely different. And this consistent 5-to-1 length ratio has held steady across earlier images. The mechanism powering these jets is applying uniform physics across hundreds of millions of miles, a stability we've never witnessed in a comet before. Typical comet activity varies wildly as ices rotate in and out of sunlight. Now, before we address the bizarre brightness, we must confront the mass loss dilemma. These tails consist of material boiling off the comet's nucleus due to solar heat, a process termed sublimation. At its vast distance, the surface of 3I/Atlas should be profoundly cold. Let's look at the numbers. Solar energy delivery weakens with distance. At Earth, we receive about 1300 watts per square meter. At 106 million miles, that plummets to around 300. But here's the critical nuance for comets. Only a tiny fraction of that energy actually turns ice into gas. The rest reflects or radiates away. For carbon dioxide ice, the primary volatile here, sublimation kicks in around minus 109 degrees Fahrenheit. Given the weak solar energy at this range, you can calculate the expected sublimation rate. The published analysis concludes that to produce the observed mass loss, you'd need about 620 square miles of surface actively sublimating at peak efficiency. But a recent image from a Mars orbiter shows the comet's surrounding coma is about 930 miles across. The solid nucleus inside, however, is only a few miles wide, granting it perhaps 30 to 40 square miles of total surface area. Even if the nucleus fills a good part of that haze, the math is impossible. You cannot get this much material from simple ice vaporization with the available real estate. Conventional science would suggest fragmentation. More pieces create more surface area. Yet, images from November show a single intact core. No swarm of fragments, just one solitary body. So, the surface area doesn't work. But the newest observations unveil another glaring anomaly. 3I/Atlas remains far too bright. Comets follow predictable dimming curves after they pass closest to the sun. As they recede and cool, their glow should fade. 3I/Atlas has been moving away for over a month. Activity should be dropping. But the November images show intense, sustained luminosity. The coma shines strongly. The tails remain prominent and sharp. Calculations indicate that to maintain this brightness, the object must be shedding about 200 tons of material every second. That is a staggering, ongoing mass loss rate for a body that should be settling down. If it has been losing mass at this rate since perihelion, billions of tons are gone. For an object with an estimated total mass of 33 billion tons, this could mean nearly 10% of its entirety has been ejected in just 2 months. A natural comet undergoing such extreme, rapid mass loss would show dramatic physical changes. The nucleus should visibly shrink. Activity should become erratic, yet none of that appears to be happening. The mystery only deepens. What's your leading theory for what we're witnessing? Let me know in the comments. If this journey into the unexplained resonated with you, please support the channel. Drop a like and follow Winds of Thought for more.